Okay, let me just do a couple solutions to some of the problems. Do them in a little more detail than I covered in the class. Maybe a little more detail in the solutions posted. So the first one is going to be problem 1.5, and these are all in Cook. All right. So here we have the following problem. There's our mesh, and I have 4 linear strain triangle elements. Go like this. Here, 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 so on and so forth. It's the afternoon. I always get tired in the afternoon, so hopefully I can do this reasonably well. Okay, and then we're putting forces on here of P and then P. What other dimensions do they give us? Well, okay, we're calling this the X direction. This is the Y direction, and we call this points A, C, and B. All right, the first part, they want you to find, in terms of beta, the strains. Okay, well, the displacement for a 6-node triangle, again, in terms of the betas, we got 6 terms because you have 6 interpolation coefficients, so it's beta 1 plus beta 2x plus beta 3y. Beta 4 gives you the byproduct, the bilinear term. Beta 5 is the x squared term, and beta 6 is the y squared term. The displacement has in the y direction has the same form, but then we're going to start out beta 7 plus beta 8 times x, beta 9 times y, plus beta 10 times xy, beta 11 x squared, and then the beta 12 term is the quadratic in y. So there's the interpolations. All right, so this is just differentiation. This is easy, but the important thing to note is that you have the quadratic interpolation in the elements, so the displacement can actually vary more than just a plane. All right, I have a difficult time kind of drawing these, but if you had to do like the interpolation out of the plane sort of picture, this will allow you to have, sort of a quadratic shape to the interpolation, if this is the interpolation of x and y, okay? Doesn't have to be a plane. All right, so the x normal stress is the partial derivative of u with respect to x, so that just gives me beta 2, and I get a plus beta 4 times y, and then I get a plus 2 beta 5 x. Okay? So you can see the strain is linearly complete. We call it complete because it has the constant the x term, and then the y term. All right? If we're missing one of these, it wouldn't be complete. Okay? But it has so this means it can reproduce any linear polynomial in strain. All right? So in fact, this allows the strain to be reproduced as a plane. Okay? Okay, we do the strain in the y, the normal strain in the y. We just take the derivative of the y interpolation with respect to y. So that gives me beta 9 plus beta 10 times x plus 2 beta 12 times y. So again, it's linearly complete. And then we can get the shear strain, and that's the mixed partial of u with respect to y plus the partial of v with respect to x. And so that gives me, the first term gives me beta 3 plus beta 4 times x plus 2 beta 6y. And then the second term from here gives me plus beta 8 plus beta 10y plus 2 beta 11x. And so this, to put it in terms of the ascending monomial terms, we have beta 3 plus beta 8. Those are the constant terms, plus beta 4 plus 2 beta 11. That's constant coefficient times x, plus 2 beta 6 plus beta 10 times y. And here again, linearly complete because we have constant linear in x and y term. Okay? So for part A, this shows that the strain field is linear in x and y. So there go linear strain triangle. The LST element as opposed to the constant strain triangle. Okay? Okay. Now if we go on to the B part, the B part is asking you, let me go find some more paper. The same picture, but part B wants us to find, it's asking us questions about how well we can use these boundary conditions to give us the exact stresses for a pure bending moment. So this is supposed to approximate the following problem, right? We're trying to, actually the moment's the wrong way. I got the moments going the wrong way. All right? Where the moment is equal to p times this distance. Call that A. All right? That's the applied moment. And in that situation, we know that the stress, the moment diagram is constant. It's just PA, okay? So it looks like this. Right? Where this is x equal to 0, x equal to L. Again, this is for the exact solution, and we're going to see if we can reproduce some results like that with the linear strain triangles. And then the stress, it's a function of x and y. That's the moment, my on I, so that gives us the following. Pa times y over I. So this is a linear polynomial in y. So basically, if you look at something like this, you should be able to reproduce this type of stress field in this element. So, for example, we know that the normal strain is going to be roughly the stress divided by Young's modulus. So that would be PA on EI times Y. Okay? Now, the lateral strain is going to be through Poisson's ratio minus nu times the longitudinal strain. So that gives me minus nu PA on EI times Y. So again, the strain field for the perfect bending is a linear polynomial. So that would correspond to, and the shear, so we're going to ignore transverse shear. We want that to basically go to 0, or I guess I shouldn't really talk about that because, for a shear beam, you'll actually get the quadratic shear over it. That will be a little difficult to show up, but let's assume that, let's talk about a situation where the shear stresses nominally go to 0. They're mostly focused in this problem and trying to reproduce these bending stresses and strains. Okay? And in that situation, this element should do a reasonable job on that. If I go and look at this, right, you can pretty much see that in each element, let's look at the strain. Okay, so to be of this form, I could get this by getting beta 2 equal to beta 5 equal to 0, and beta 4 equal to PA on EI. All right? Now I can get this. Let's look at the Y strain. Okay? Right? I would recover this if beta 9 equals 0 and beta 10 is also 0, and then that beta 12 is minus new PA on 2, because I have the 2 beta 12 here, EI. Okay? So if I construct it, if I pick the nodal displacements such that these come out to be the betas, all right, this element should be able to exactly reproduce that linear strain field. Now, you cannot do the same thing with a constant strain triangle. Remember, if we look at the strain in the x direction of the constant strain triangle, it just becomes beta 2. So there's no way I can set beta 2 to ever get this response that's a function of y, okay? Or this one, right? There's nothing I can do to beta 2 to get that to work, all right? So the constant strain triangle will not give you that. You only allow it to reproduce it approximately by adding more elements, okay? Okay. Now, I've picked almost everything except for beta 1 and beta 7, but those don't really enter into the strain anyway. But let's look at how, knowing these values, let's see how that would impact the shear strain. Okay. The shear strain would be beta 3 plus beta 8. I have no conditions on those. So those are free. Beta 4 and beta 11. Again, those are also not constrained by this. Beta 4 plus 2 beta 11. And then on the Y term, I got beta 6 and beta 10. And here I have beta 10 has to be 0. Is that right? Yeah, beta 10 has to be 0. Nothing else can be beta 6. I think beta 6 should pop up somewhere as well. I think I got that right. I guess that's right. Beta 6 doesn't pop up because beta 6 is only a shear term. Right. Okay. And so what do I get here? I know beta 10 has to be 0, so this just gives me 2 beta 6 times y. Okay. So if beta 3 equals minus beta 8, and then beta 4 equals beta 4 plus 2 beta 11 equals 0, and then 2 beta 6 equals 0, or beta 6 equals 0. This will basically get all the shear terms to roughly go to 0. It will nominally get small shear, so you can actually consider small shear also reproducible in this element. So you can actually get a low shear strain. Now, in practice, we do know that the shear strain has the following form. It's V, Q on I, T, right? Where Q actually is a function of the cross-sectional area, right? Remember, if here's the neutral axis, Q is basically the first area moment of the area above the point of interest. Okay? But this tends to give you, without working through all the details, you know that this gives you a parabolic shear distribution. Okay? It's V is constant. Well, actually, in this element, the V is 0, so it drops out. But in general, if you have a non-zero V, you'll get this quadratic distribution. And what you can see, though, is that, again, because this cannot reproduce a quadratic, it can only reproduce linear, you will not be able to exactly reproduce the shear terms that arise from bending. Now, those are usually small, but when we look at planar elements, we will see that, in fact, this will cause us some difficulty, okay? But it's not really what they're asking in this problem, okay? So we'll stop there. Okay. They also ask about the supports in problem B. Why do you pick these supports? Well, again, that is to allow free lateral contraction for a Poisson effect. So that pretty much finished off B. Now, part C asks for an alternate arrangement. So part C would ask for an alternate arrangement. Well, really, any type of arrangement that allows free lateral contraction will work. So you could actually, on this edge, if this is the points A, C, and B, you could pin the top and put the bottom ones on rollers. That would work. You could also, well, put the top two on rollers and pin the bottom. The point is, oops, I put this fixed thing in the wrong way. This is fixed, okay? The point is, in all these configurations, you only fix one point completely at X and Y, and you allow the other two to smoothly move up and Y to contract freely. It doesn't matter which point you fix, okay? The other way you want to think of this is, we'll talk a little about this later on as well, is you want to minimally constrain it to reject the rigid body modes. Now this is a little more than that actually, but so you pin one point. As soon as I take a body and I pin one point, it can't move in X and Y, but it can rigidly rotate. So then you take something, usually if you pin something and put a roller at one point, that will kinematically constrain it. Now, where you put the roller and the pinpoint will have an effect on the stress distribution. In this particular case, these are equivalent to this, and you'll get the same thing. Both of them, this one will be fixed here and allow these things to freely move up. This one will allow these to freely move down, okay? And so you won't have any force constraining those. All right. Probably didn't say that in the most clear way, but it's usually the best I can do. If you ask me offline, I can probably describe it in a better way for you if you want. Okay, let me pause now because I think we're going to run out of time for